Hey friends, Dr. Borole is here. Today we will see the arithmetic operation in various number systems. First we will see the arithmetic operations in binary system. Let us study the binary additions. Here figure 1 shows a truth table for addition of two binary bits. There are 4 rules. Since there are 2 bits in the addition, there are 4 combination exist. For example, number A and number B are the binary numbers. When both the bits are 0, the binary sum will be 0 and carry will be 0. When bit A is 0 and B is 1, then sum is 1, carry is 0. When A is 1 and B is 0, the sum is 1 and carry will be 0. When both the bits are 1, that is 1 plus 1 is 0, that is the sum, and carry is 1. Means when two bits are 1 plus 1, then sum will be 2 bits. So 2 single bit addition, when overflows, it generates 2 bit sum. One is the carry bit and another is the sum bit. When multi-bit binary addition is to be done, then it is similar to our conventional multi-digit decimal number addition. We will add the bits of the two binary numbers column by column. Let us take the example. Suppose there are two numbers A and B with the bit number B0 to B4. Then the binary addition can be done column by column. Say for example, bit 0, B0 here is the bit 0 of number A is 1 and bit 0 of number B is 1. So 1 plus 1 is 0. That results to sum 0 and carry 1 here. In the second column, this carry is 1 plus number A is 1. So 1 plus 1 plus 0 is 0 plus carry 1 again. Again in the third column, 1 plus 1, 0 plus carry 1. In the third column, this carry plus the third bit of number B, that is 1 plus 1, is 0 again and carry 1. Now in the fourth column, you will see that both number A and B have bits B4 as 1. So 1 plus 1 plus carry 1 is 1 1. So sum is 1 and carry is 1. So 5-bit number is now getting the summation as 6 bit. Out of that, lower 5 bits are the sum bits and the last MSB is a carry bit. Now binary subtraction. Again we will see the rules of subtraction. Here the table shows the rules of single bit binary subtraction. Number A and number B are the single bit binary number. When both the bits are 0, 0 minus 0, subtraction is 0 and borrow 0. 1 minus 0, subtraction is 1 and borrow 0. 1 minus 1, subtraction is 0 and borrow 0. 0 minus 1, the borrow is 1 and the subtraction is 1. When multi-bit subtraction is to be done, it is again done similar to the multi-bit addition. Here only we apply the rule of subtraction and we do the subtraction column by column. So number A and number B are shown here. B0 to B4 are the bits of the number. In B0 column, 1 minus 0 is 1. In B1 column, 1 minus 1, the borrow is 0 and subtraction is 0. In B2 column, 0 minus 1 is give you the borrow 1 and subtraction 1. This is the last combination shown in the table here. In a B3 column, here you will get 1 minus 0 minus 1 is 0, subtraction is 0 and borrow is 0. In B4 column, 1 minus 1 is 0 and therefore the number A 11011 minus number B 10110 gives rise to the subtraction 101. No borrow is generated, so number is positive and number A is greater than B. You can make the practice of adding multi-bit binary number with the following exercises. It is left to you as home exercises. Some of the questions those are asked in the examination are now considered. Add and subtract decimal number 26 and decimal number 32 after converting them to the binary numbers. Means there are addition of the two numbers and then you have to perform the subtraction of the two numbers, and that is to be done by converting them to the binary number. Here in step 1, both the decimal numbers are converted to the binary number by the double-double system we have already seen. When any number, decimal number is to be converted to binary, it will be successively divided by 2 and the quotient will be successively divided by 2 and the remainder will be noted in each step, and the process will be continued till the quotient becomes 0. Once the division process stops, then the last MSB, remainder will be the MSB and the first remainder will be LSB. So in short, we can say go on dividing the number by 2, note down the remainder. When the process ends, write the number from bottom to top as MSB to LSB. So we will convert, we have convert here 26 to number 11010 binary, and we have converted number 32 decimal by successive division by 2 to a binary number 100000. Now both the numbers we got. So in second step we will perform addition of the two numbers. So we will write the number column by column and add the number. 0 plus 0 is 0, 1 plus 0 is 1 here, 0 plus 0 is 0, 1 plus 0 is 1 again, 1 plus 0 is 1 again, and 0 plus 1 is 1. So sum is 110010. If you convert this binary number to decimal again, you will get the number 58 decimal, and which is also verified as 26 plus 32 in decimal is 58. Now perform the subtraction. In the subtraction we take again the two numbers, 32 as number 1 and 26 as number 2. And we will subtract the two numbers column by column and we get here bit by bit subtraction, and the result will be 0 0 0 1 1 0. Right. Here the 32 minus 26 is 6. Here it is wrongly printed at minus 6. Therefore, here also you will get the result, binary result 110. 110 corresponds to decimal number 6. We will make the correction, this typo correction in this problem. The minus sign will be not there. If you do the reverse procedure, 26 minus 32, then the result again same, and you will get the borrow generated here, and that indicates that the number is negative. The next operation, arithmetic operation, is binary multiplication. The rules of the multiplication in binary are very simple. For example, if two bits are to be multiplied, say bit 1 and bit 2, say A and B, then 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, and 1 into 1 is 1. Means anything multiplied by 0 is 0, and 1 multiplied by 1 is 1. When you want to perform multi-bit multiplication, the procedure is very similar to decimal multiplication, but it is very easy in binary, because in binary there are only two state values, logic 0 and logic 1 for the bits. This algorithm of multiplication is also called as shift and add algorithm, to which we are very familiar in decimal number system. Now let us see how to apply this generalized algorithm to binary multiplication. Suppose first number is A0 to A3. Say A0, A1, A2 and A3 are the 4 bits of number A. That is to be multiplied by the multiplicand number B, that is B0, B1, B2, B3. So what we do normally in the multiplication, we will multiply bit by bit. So first we will take a bit B0 and multiply number A, that is A0, A1, A2, A3 by bit B0. So therefore, when B0 multiplies A0, it is A0 B0, then B0 into A1, A1 B0, then B0 into A2, A2 B0, then A3 B0. So that is the first term you are getting, right? Then we will multiply the number A by using number B1. But this number B1 is at the second position from left. We will shift the partial sum by one position. So here we will shift the partial sum by one position and then multiply number A with B1, and we have written it here, right? So similarly, in the third step, we take number B2 and then B2 multiplies all these 4 bits. Since B2 is in the third position from left, we will shift the partial result by 2 positions and write the multiplication that is generated by B2. Then last bit B3, we will multiply the number A again by B3. Now this bit is at the fourth position from left, so we will shift the partial product by 3 positions and then write the partial product. After writing the partial product, we will column by column add this partial product, and the result will be obtained, and that is the multiplication of the two numbers. Let us take a real example. Multiply 9 that is binary 1001 by decimal 8, that is 1000. So number A is 1001 and number B is 1000, shown here. 1001 is multiplicand and 100 is a multiplier. Now consider the B0 bit of the multiplier. So this 0. 0 is multiplied by 1001. The partial product is 0. So we have written the partial product 0000. Now we will take the bit B1, that is also 0. We will shift the partial product, and the partial product 1001 into 0 is 0. Again we will add this partial product by shifting it left by one position. Bit B2, that is also 0, therefore partial product is 0. We will shift it by 2 position and then add. The bit B3, which is 1, and that is again multiplying 1001. The partial product is 1001. Again it will be shifted left by 3 position and added. Then column by column we will perform the addition of all these partial products, and we get the final answer 1001000. That is the multiplication of the two binary numbers shown here. And this number is corresponds to decimal 32. That is binary equivalent of decimal 32 is 1001000. The binary multiplication of the fraction can be performed on similar tracks. Initially we will not consider the binary point. We will do the multiplication bit by bit to the total bits in the number A by number B. Every time we will shift the partial product by one position. We will generate the column by column addition, and then we will put the decimal point. Since here the decimal point in number A is after 2 positions and in B the decimal point is after 2 positions. So total number of positions the decimal point will be shifted left in the result are 2 plus 2, that is 4. So therefore we will put a decimal point after 4th position. If you consider as 0 base position, then this is B0, B1, B2 and B3. After B3 we will put here the decimal point, and therefore the result will be 101001.1011. The same procedure we are following for the decimal multiplication. Here, since the binary number have only 2 states, the product will be either the number itself or 0, that can be a partial product. So therefore the multiplication is very simple. The next arithmetic operation is binary division. It is also called long division method, and it is also similar to the decimal division we are following. Let us consider the number. The dividend is 110 and the divisor is 10. So binary number 110 will be divided by the binary number 10. So write it like this. Here the dividend is written 110 and divisor 10 is written. Now take a quotient of 1. 10 will be 10 will be subtracted from 1. Column by column we will subtract. 1 minus 0 is 1. 1 minus 1 is 0, and therefore the remainder will be 1. Then next take the next digit on this subtracted result, subtraction. Then the number becomes 10 now. Now divisor is again 10. It will give the quotient of 1 again. So 10 into 1 is 10. 10 minus 10 is 00. And therefore you are getting the quotient of 11. that is corresponds to decimal 3. 10 corresponds to decimal 2 and 110 corresponds to decimal 6. And therefore, if you check in the decimal division, 6 by 2 is 3, and here the binary division also shows the same thing. Here somewhat more number of bits are considered. Here divisor is 101, so we will consider first 3 bits. 110 divided by 101. The quotient will be 1. We will subtract 101 from 110. The remainder will be here 1. We will take 1 on it. Then the sub remainder will be 0011. Divisor is higher, so quotient will be 0. Again, we will take the next bit down. So we will get the sub remainder as 111. Now divisor is less than this number. We will have a quotient of 1. We will subtract from 111 101. We will get the subtraction as 010. Then we will take the last digit of the binary number on this remainder. So remainder will be 100. Since this 100 is less than the divisor, the quotient will be 0 and remainder will be 100. And therefore you will have a quotient, final quotient as 1010, divisor 101 and remainder 100. 100 corresponds to 4. 1010 is 10 and 101 corresponds to 5. So 5 into 10, 50 plus 4. 110 is corresponds to 54 decimal. So one thing to be noted here, that when you perform the integer division, then decimal point position will be decided by the position of the decimal point in the dividend. Whereas division of decimal by integer, then decimal point position will be decided by the position of the decimal point in dividend. When the division of decimal by decimal, then convert the divisor to integer. Means always the divisor is made integer by shifting the decimal point to right in both numerator and denominator, and then perform the long division and use the case 2 to decide the decimal point of the division. These rules are exactly same as the rules of decimal additions. So that's all about the arithmetic operation with binary numbers. The types of numbers in any number systems have following characteristics. The system may be decimal system, binary system, octal system or hex system. The first category of numbers are terminating decimal numbers. Means they can have the fixed number of digits like 34.9807. After that the digits are 0. 55.5 or 55.5000 means the value will be fixed and there is no digit in continuation. Non-terminating decimal number. These numbers are indefinite numbers and they will be continued at infinite number of decimal places like 25.214212 dash dash dash. It will be continued like the value of root 2 or like the value of pi. The number generated is continued up to infinity. These are called non-terminating decimal number. Recurring decimal number. The numbers in which The number combinations are repeated indefinitely called recurring decimal numbers, and non-recurring decimal numbers in which the numbers are continuously present up to infinity in the fractional portion, but they are non-terminating. The number representation used in the binary system are of two types: signed numbers and sign magnitude numbers. The signed numbers have sign. In decimal number, signed decimal number, normally we are using plus and minus sign to indicate the positive and negative decimal number. Whereas in digital circuit there are only two symbols, 0 and 1. There is no plus and minus sign. Therefore, in digital electronics, normally for plus and minus indication, one MSB is attached to the number, and that MSB bit is indicating the sign. Normally, bit, if it is 0, then it is considered as a positive number, and if this MSB is 1, the convention is it is a negative number. Whereas this is a convention. This convention, once accepted, we have to follow it throughout the circuit and take care of sign representation of the convention. Otherwise, electronic circuit doesn't understand a bit and sign. Sign magnitude representation is another form of representing the number. So in sign magnitude number, as we discussed, one bit is reserved for the sign and remaining lower significant bits are used for magnitude. The MSB is reserved for sign and remaining bits are representing the magnitude. Let us see the example. Here it is a 8-bit number. Out of that, MSB is reserved for sign in sign magnitude number, and remaining 7 bits indicate the magnitude. When the sign bit is 1, the number is treated as negative number, means that magnitude is considered as a negative magnitude, and when sign bit is 0, the number in the magnitude is treated as positive number. Here the typical number is 0000100, that is corresponds to 4. But sign bit is 0, means it is minus 4. And in the second representation, same magnitude is with 0 sign bit indicates the number is plus 4. So here another example you will see. The 8-bit number shown here. Total number of bits are 9. So in this example, the 8-bit binary number with 7-bit magnitude and MSB is reserved for the sign bit. Here the number 73 is mentioned. 1001001 in binary corresponds to 73 decimal. The 73 represents the magnitude and the MSB 0 indicates the sign. So total number including sign is 8-bit. Out of that, 7-bit is magnitude and last MS digit is indicating the sign. Similarly here, the same number with MSD or MSB as 1, it indicates the magnitude is decimal 73 with sign negative. So it is minus 73. This type of representation of the binary number is called as signed magnitude number. The signed number representation can be alternatively given by the complement representation, that is ones complement and twos complement of the binary number. It is different than the sign magnitude number, but ones complement and twos complement of the number are the negative numbers. For example, let us see how ones complement work. If the binary number is given, then if you complement each bit, complement means if the bit is 0, then make it 1. If the bit is 1, make it 0. So like here, the binary number given 1011010, then we will see here, start from bit B0, here B0 is 0. If we take the ones complement, we complement each bit of the number. So 0 becomes 1, 1 becomes 0, again 0 becomes 1, and so on. So here complementing each bit position to its opposite state gives you ones complement. If you add 1 in that, then it will be converted to twos complement. So let us see ones complement plus 1. When you add 1 here, 1 plus 1, 0, 0 plus 0 plus carry 1 is 1. Then 0 plus 1 plus 0 is 1 again. 1. This 0 plus 0 is 0 again. This 0 plus 0 is 0 again. 1 plus 0 is 1 again, and 0 plus 0 is 0 again. So complement plus 1 gives rise to twos complement. And simple way of making the twos complement of a number by observation is just go on complementing the bits of the number from left, means from MSB, till the last one occur in the LSB position. So here the 1 occurs in B1 position in the number. So up to B3 position we complement all the bits. Say 1 becomes 0, this 0 becomes 1, then this 1 becomes 0 0, then this 0 becomes 1. So we complement all the bits up to B3 position, and the last one will be kept as it is, and remaining number after that on right hand side will be kept as it is, and that will give directly the twos complement number. Otherwise the procedure is simple. Take the number, take the ones complement by complementing each bit, add 1 to it, and the result you are getting is a twos complement number. Ones and twos complement numbers are representing the negative numbers. The main difference between ones and twos complements are the ones complement has two representation of zeros. 0 0 0, which is positive 0, and 1 1 1 is a negative 0. And this makes a trouble in handling the arithmetic of ones complement number. And therefore twos complement is very popular. In twos complement representation, there is only unique representation of 0. That is, all bits 0 is 0, all bits 1 is negative side, negative number, and all bits positive is a positive number. And this is why the twos complement is generally used. Let us have an example of ones complement and twos complement number. Suppose given number is 10110010. What is the ones complement? Just invert each bit. 1 becomes 0 and 0 becomes 1. You are getting ones complement. Add 1 to this ones complement. Column by column you can add the binary bits and whatever you get is 2's complement number. Let us see what are the differences between sign magnitude number and 2's complement number. This is the optional thing. This is not there in the syllabus, so we will go somewhat fast. In sign magnitude number, the most significant bit indicates the sign and remaining bits are indicating the magnitude. Whereas in 2's complement number, the sign bit is the MSB and remaining lower bits are representing the magnitude. Only difference is that if you see here the magnitude 100 corresponds to magnitude 4, but in 2's complement number the negative number, when the sign is 1, this 1 is extended to the last position of 1, and therefore all bits after this B2 position, that is B3, B4, B5, B6 and B7 are extended indication of the sign bit. Whereas for positive numbers, since the bit is 0 for sign, the remaining bits after the last significant one are extended by zeros. Okay. The various differences are listed in the table, but since they are optional, we will continue to the relevant topic of our syllabus. Now let us see the arithmetic operation that can be performed by using 1's complement and 2's complement. The binary subtraction using 1's complement. Now we know in any system, like in decimal system also, addition of a negative number is basically performing a subtraction. Whereas 1's complement and 2's complement of a number is a negative number itself. So adding 1's complement or 2's complement in any number perform the subtraction of the two number. So 1's complement can convert the subtraction to addition of the 1's complement in the number 1. The procedure for performing the 1's complement operation is summarized here. Then we will see the example. If you have two numbers, say, to be subtracted, then convert the number to be subtracted, say B2, to 1's complement. We want to subtract this number from, say, number A2. Then add 1's complement of B2 to number A2. If carry is generated, then add this carry back to the subtraction A2 minus B2. And if carry is generated, A2 minus B2 subtraction is positive, means A2 is more than B2. If no carry is generated, then the subtraction A2 minus B2 is negative. And in the 1's complement form, A2 minus B2 is negative, means the representation remains in 1's complement form. To convert this into true form, then we have to take the 1's complement of the result. Let us see. Decimal 9, from which the decimal 4 is subtracted. This is given in decimal, but we want to perform the subtraction in binary using 1's complement. So first convert the number 9 to its binary representation. Then convert the number 4 to its binary representation. And then first take the complement of 4. 4 in binary is 0, 1, 0, 0. Take a complement of it. Complement each bit. So after complementing, 0 becomes 1. So 1 0 1 1 is 1's complement of 4. So in second step, we will add this 1's complement in the binary representation of 9. Binary representation of decimal 9 is 1001. Minus we got the 1's complement 1011. So we are going to add this 1's complement in 9. So ultimately adding 1's complement results in subtraction because 1's complement is a negative of a number. Now we will do column by column addition. 1 plus 1 is 0. 0 plus 1 is 0. 0 plus 0 is 0. 1 plus 1, the sum is 0 and carry 1. If carry is 1, then we have to add this carry back to the sum. So this carry here will be taken and added to the B0 column, bit 0 column. Now this becomes 0 1 0 0 plus 1 and that becomes 0 1 0 1. And that is the answer. Since carry was generated, the answer is positive. So ultimately 9 minus 4 is 5 in decimal. And here after 1's complement addition and adding back the carry here, we are getting the result 0 1 0 1, that is corresponds to decimal 5. And the answer is in positive form. Now let us consider reverse. Suppose the first number is less than the second number. We want to subtract 9 from 4. We know the first number 4 means 0 1 0 0. The binary representation of 9 is 1 0 0 1. Take a complement of it. Complement each bit. So it becomes 0 1 1 0. Now this complement will be added here in the next step in binary representation of 4. Column by column addition, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0, carry 1. Say 0 plus 0 plus that carry, the result is sum 1 and carry 0. So there is no carry generated. When no carry generated, it means answer is negative. And this negative answer is in 2's complement form. To convert it to the proper magnitude, we have to take the 1's complement of this number again. So take a 1's complement of this result 1010. Take 1's complement, invert all the bits. 1 becomes 0, 0 becomes 1 here, again 1 becomes 0 and 0 becomes 1. So answer is 0 1 0 1. 0 1 0 1 corresponds to 5. But since no carry was generated, this answer 5 is with negative sign. So it is minus 5. And obviously 4 minus 9 is minus 5. That is shown here. Binary subtraction using 2's complement method. 2's complement method simplifies the subtraction a bit compared to 1's complement, because there is only one representation of 0 in this 2's complement method. The procedure is simple. If we want to subtract number B2 from A2, then what we do? We will take the 2's complement of B2, that is the second number, and add this 2's complement in the first number, that is A2. If carry is generated in the addition, then subtraction A2 minus B2 is positive. If carry is not generated, then subtraction A2 minus B2 is negative. And if it is negative, then it is in the 2's complement form. To convert it to the true form again, we have to take the 2's complement of the result. So this is the simple 4-step procedure. Let us see the example. Suppose we have binary number 1101. and we want to subtract 1001 from it. So second number is 1001. We will take a 2's complement of this number. 2's complement of 1001 can be obtained by inverting all bits first. We will get 1's complement and then add 1 to it. So we will get 0110 as 1's complement and add 1 to it. So you are getting 0111, right? So that is the 2's complement of number B. Next step is add this 2's complement to the number A. So number A is 1101. We have a 2's complement of B, that is 0111, and we can add this to column by column. So 1 plus 1 is 0, carry 1. So again 1 plus 1 is 0, carry 1. Now here 1 plus 1 is 0 plus 1 is 1 1, means sum is 1, carry is 1. Again 1 plus 1 is 0, sum is 0, carry is 1. So here the carry is generated at the 5th position. So therefore if carry is generated, means answer is positive. Means 1101 minus 1001 gives rise to the result 0100, and the answer is positive. There is no need to do anything further because number is already positive. Now let us take another example. Suppose decimal 52 from which 65 has to be subtracted. So first we are going to convert 52 and 65 to the binary form. Then we will take 2's complement of 65 and then add this 2's complement of 65 in the binary form of 52. Then column by column addition we will do and then check whether the carry is generated. Here from the decimal subtraction we understand that there is no carry generated, means answer will be negative. Let us see. So 65 we have taken, the binary value of 65 is 1000001. Take a 1's complement, means complement each bit, you are getting this number. Add 1 to it, you are getting the 2's complement of the binary number 65, that is this. Then we will, in second step, we will add this 2's complement of 65 in the binary value of number 52. Column by column we are going to perform the addition and we will get the result, and finally we observe in the last column that there is no carry generated. In 2's complement arithmetic or subtraction, we have already listed above that when there is no carry generated, the answer of the subtraction is negative and it is in 2's complement form. So converting this result back to the sign magnitude form by taking the 2's complement of this result. So 2's complement can be obtained by adding 1 to the 2's complement again. Subtracting 1 to the 2's complement again. So we have subtracted 1 from the 2's complement, which is the answer. We got the 1's complement and we will invert the bits of this 1's complement. You are getting the original magnitude of the number. Since the carry was not generated, this magnitude will be negative. And therefore 52 minus 65 is coming out to be 13. But 65 is more than 52 by 13, and therefore we represent this sum by minus 13 decimal. The complement operations are available not only in binary system, but complement operation are available in decimal system and hexadecimal system and octal systems also. The nines and tens complement can be used for performing the subtraction of two decimal numbers in decimal system, whereas sevens and eights complement can be obtained by performing the subtraction in octal system, and 15 and 16's complement can be used to perform the operation in hexadecimal system. But and the procedure is same again, like binary ones complement and twos complement. But since it is beyond the scope of this subject, it's an optional topic, and therefore interested reader can study that for their general knowledge. In your examination, 7 complement, 9's complement, 10's complement or 15 and 16's complement are not focused. Now we will see the next system arithmetic operation, say octal arithmetic addition. Some thumb rule can be remembered. These are the summary of the operation. If decimal column sum is less than 8, then sum will be in the octal form. If the decimal column sum is greater than 8, then sum will be not in the octal form, because in octal form the number of symbols used are 0 to 7. So 8 is not present in the octal. So anytime the summation results to 8 or higher, it is not in the octal form, it is in the decimal form. So we have to subtract 8 from it to bring the decimal result to the octal form again and generate a carry. Let us see the example. Suppose 2 plus 4 octal numbers are added. So 2 plus 4 are 6. The sum is less than 8 and therefore the sum is already in the octal form. Let us see the second example, 7 plus 4. So 7 plus 4 is 11 in decimal, but 11 is not there in the octal form, right? Octal numbers are up to 0 to 7 only in one digit position, and therefore this sum needs to be corrected by subtracting 8 from it. So 1 minus 8 is equal to 3. So as shown below, 7 plus 4, it gives you 3 plus carry 1, right? So 13 is the result of 7 plus 4. 1 3 will be the result of say addition of the two octal number. So if you have multi-digit number, then you can very well perform column by column addition. For example, 634 octal can be added to 152. 6 plus 2 here, last column, 4 plus 2, that is 6. So the number is always less than 8, so it can be continued as it is. Then second column, 5 plus 3, 8. This number is not in the octal number format, because octal number have 0 to 7 digits only. So what is the solution? We have to subtract 8 from it and generate a carry, right? So we will generate carry 1 here and subtract 8 from this. So 8 minus 8 is 0 and carry generated will be here. Now 6 plus 1 plus 1, total is 8. Again this number 8 is not in octal form. So what we have to do? We will take a carry and the number becomes now 10. From 10 we will subtract 8 minus 8. The result will be 0 and carry will be taken to the next column. And this carry will be written as the fourth bit. So result will be 1006. That is corrected form in the octal numbers. Whereas if you directly add the two numbers, the partial result will be 886. But this 886 is not in the octal form because here two digits are equal to 8 or greater than or equal to 8. So you need to generate a carry and subtract 8 from it to bring it to the correct octal form. Here three numbers octal addition is shown. Rule is same again. Go on adding the digit column by column. Here first column 6 plus 4 plus 6 plus 3, total sum is 13. 13 is not the octal number. Therefore we will generate carry to the next column and subtract 8 from it. So 13 minus 8 is 5 and carry is considered here. So 5 plus 6 plus 2 plus 1, that is 14. Again 14 is not in the octal form. Subtract it. It is greater than 8 and therefore subtract 8 from it and generate a carry. So carry will be taken in the next column. So 3 plus 2 5 plus 1 6 plus 1 7. 7. This is less than 8 and therefore it is in octal form. So this will be taken as it is to the result. So final result will be 567, means 765 is a octal number. So if these three numbers are added, the result will be 765 in octal. The octal number subtraction using 7s and 8s complement method are not there in the syllabus, but direct subtraction is covered here. And the octal number subtraction can be done in two steps. First, convert octal number to binary. Then binary subtraction will be performed. And then converting the result back to the octal. So direct method we will see. It is same as the decimal subtraction. The borrow is taken when minute is less than the subtrahend. The borrow from next column is 8 instead of 10. In decimal, the borrow will be 10, whereas in octal number, the borrow will be 8. Now, 75 minus 68, octal number subtraction. Here it is written, A is 75 minus 68, that is in octal. 5 minus 8. The subtraction is not possible. So what we will do? We will take a borrow from the next column. So we will take a borrow. But here the number system is the octal number system. So borrow is 8 instead of 10. So 8 plus 5, 13. 13 minus 8, that is 5. Already we have taken a borrow from this. So 7 minus 6 minus 1, that will be 0. So 75 octal minus 68 octal is 05 octal. If you consider example 2, it is a 3-digit subtraction. The same thing again, you will write the numbers, number A 653 minus number B 177. If you see the last column or least significant column or digit 0 column, 3 minus 7. The subtraction will not take place. So we will take a borrow from the next column. And borrow is 8. So 8 plus 3, 11. 11 minus 7, that is 4. We have taken the borrow, so we mark it here. 5 minus 8. Again, subtraction will not be possible. So we will take a borrow from the next column. So 8 plus 5, 13. 13 minus 8, that will be 5. Borrow is noted here. 6 minus 1 minus the borrow, that is 6 minus 2 is equal to 4. And therefore 653 minus 177 is equal to 454 in octal. The octal multiplication is shown next. But we have to have some light on subtraction of the octal number by conversion, second method. And this method is simple. Basically, the octal number will be first converted to binary numbers, and then binary subtraction can be done in the conventional way, or by 1's complement subtraction or 2's complement subtraction we have seen earlier. And then from the binary result generated, we will convert binary number to back to the octal number. So it is a three-step procedure. In octal multiplication, convert multiplier and multiplicand from octal to binary first. Means always convert the numbers to the binary form, perform the binary multiplication, that is shift and add algorithm, and then result will be converted back to the binary number. We have already discussed about the binary multiplication and conversion of octal number to binary number in the previous lectures. So student can do the multiplication accordingly. Octal division, again on the similar ground, we will first convert dividend and divisor from octal to binary, then perform the binary long division, and then result, that is quotient and remainder, will be converted back to octal. Now the next arithmetic operation is the hexadecimal operation. Arithmetic operations of octal numbers are not very popular. Only binary and hexadecimal and decimal operations are very commonly used in the systems, whereas binary and hexadecimal arithmetic operations are quite common in digital electronics and computer science engineering. Octal arithmetics are just remains in the theory. So hexadecimal addition. Hexadecimal addition is same as their equivalent decimal number addition. If decimal sum is less than 16, the sum will be in hexadecimal form. And if the decimal sum is greater than 16, then you have to subtract 16 from it to get the hex digit. And carry has to be generated, that is equal to 1. Let the number 8 in hexadecimal form is added to number 5. So 8 plus 5, do the plain decimal addition. So 13 in decimal, 8 plus 5 is 13 in decimal. And from the conversion table we have studied earlier, 13 corresponds to D. This H indicates the hexadecimal number. Whereas here the number is less than, or addition is less than 16, and therefore whatever the result, that result is in hexadecimal form only. So result is D. H indicates the subscript. That is the notation for hexadecimal number. Let us see 9 in hexadecimal added to 8. Add it in decimal. 9 plus 8 is 17 in decimal. But now 17 is greater than the maximum number in hexadecimal system, that is F, that is corresponds to 16 in decimal. So therefore, to bring it back to the hexadecimal form, we have to subtract 16 from this sum and generate a carry. So here 17 minus 16, that is 1, and carry is generated. So hex sum will be result 1 and carry 1. So result will be 1, 1 H. So two single digit number getting added generates the 2-digit hexadecimal number. The lower significant digit is 1 and carry is 1. So 1, 1 H in hexadecimal is 17 in decimal. You can convert 1, 1 H to decimal. That can be 1 into 16 to the power 0, that is 1. and second position 1 into 16 to the power 1 means 16 into 1 plus 1, that is 17. The third example indicate the addition of two hexadecimal number of 2 digit C2H and 3EH are added. H indicates the hexadecimal digit here. So first convert each digit of the hexadecimal number to decimal number. So C2, C will be converted to 12 decimal and 2 is converted to 2 in decimal. 3E, 3 as it is in decimal and E corresponds to 14. So here do the addition, 14 plus 2 16, the result is greater than 16 and therefore correction is required. So as usual we have to subtract 16 from it and generate a carry. So 16 minus 16 is 0, carry is generated here, that is taken, right. So next column here 12 plus 3 is 15 plus 1 16, again 16 is greater than the last number in hexadecimal system, that is 15, and therefore we have to make the correction by subtracting 16 from it. 16 minus 16, result is 0 and carry will be generated, and then we are taking carry as MSB and the partial additions we have that as it is taken. So 100 will be the answer of adding these two hexadecimal number. Example 4 shows 4 digit hexadecimal addition. Students are recommended to go through the procedure. It is same. When the number is greater than or equal to 16, it needs correction. So when sum is greater than 16, you have to subtract 16 from it and generate a carry to the next column. The subtraction will be continued to the final result. So here in this second column, the first column generates the carry 12 plus this 10 plus 1, total 23, and 23 is greater than 16, therefore we have to subtract 16 from it. 23 minus 16 is 7, carry has to be generated and that carry is to be considered in the next column. Likewise you have to continue and then write the number with final carry. Hexadecimal subtraction operation, it can be done directly in hexadecimal itself, or you can do it by converting the hexadecimal number to binary and then perform the binary subtraction and then convert the result back to hexadecimal. Binary subtraction is shown here. First number is A and second number is 8. A is corresponds to 10 decimal and 8 is 18 decimal. So 10 minus 8, that is 2. The result is less than 16 and therefore it is in hexadecimal form. Take another example, 73 minus 1C. See the lower significant column, 3 minus C. 3 corresponds to decimal 3 and C corresponds to decimal 12. So 3 minus 12, not possible, therefore we will take a borrow from the previous column. So 16 plus 3, now 19. 19 minus 12, result is 7. We will consider the borrow in the next column. So 7 minus 2, so 5. So 57 is the result. Hexadecimal multiplication is the next operation. The best way to perform the hexadecimal multiplication is to convert both multiplier and multiplicand in binary form from the hexadecimal form and perform the simple binary multiplication by shift and add algorithm, and then final multiplication will be converted back to hexadecimal form. So the following example shows the shift and add algorithm. The students are familiar with it. We have already done this binary multiplication earlier. The final binary result of the multiplication is here. That can be converted back to hexadecimal form By the simple method we have already studied, binary to hexadecimal conversion, we will group the binary number in subgroup of 4 bit each, and correspond to that group we will write the corresponding hexadecimal number. So here we will see the last group 0010, that is corresponds to 2, 0110 corresponds to 6, 101 corresponds to 9, and 001 corresponds to 1. So 1962 is the corresponding hexadecimal number. Hexadecimal division, again like multiplication, division can be done in binary form. So first convert hexadecimal numbers, the divisor and dividend, to a binary form from hex, then perform simple binary division, and then convert the quotient and remainder from binary to hexadecimal number by grouping quotient and remainder in the group of 4 bits. The BCD arithmetic. BCD arithmetic, basically the BCD numbers are the binary representation of the decimal number 0 to 9, and BCD numbers are represented by 4 bit combinations. So for example, number A is 1010 and number F is 1111. These are the numbers not present in the decimal form, and therefore the combination 4 bit combination A to F are invalid. Only 0 to 9 combinations are valid combination in BCD addition. Refer back the conversion table. The rules of the BCD summations are same as the arithmetic summation in decimal numbers. If sum is less than or equal to 9 and carry is 0, this is one condition occur. Sum greater than 9 and carry is 0, this may be another condition occur in this summation. Sum less than or equal to 9 but carry is 1, these three condition occurs. So let us see one by one. Sum less than or equal to 9 and carry is 0. The number is valid number. Let us see. First number is 2 and second number is 6 in decimal. The equivalent BCD number corresponds to 2 from the table is 0010. And for 6 it is 0110. Do the column by column binary addition. The result is 1000. 100 corresponds to the digit 8 in decimal, and it is a valid sum. It is less than 9 and therefore carry is not generated also here. So carry is 0 and sum is less than 9. So number is already in valid BCD form. Now let us consider the second case. 7 plus 6. 7 corresponds to 0111 and 6 corresponds to 0110. Do the column by column addition. The result will be 1101. Now 1101 is equivalent to 13 decimal. Whereas in BCD we know only up to 9 combinations are there. Any combination after this, that is 1101, this is an invalid BCD combination. So to correct this combination, we have to add 6 BCD in this invalid number. So we add 6 here. 6 corresponds to 0110. After addition, you will get, say 1 plus 0 is 0. 0 plus 1 is 1. Here 1 plus 1 is 0, carry 1. And therefore 1 plus 1 is 0, again carry generated here. So therefore the correction is done and carry is generated here. Then the final answer will be therefore of 2 BCD numbers, that is 001 is the most significant BCD number and 0011 is the corrected BCD result, and that is corresponds to 13. You can check out this 4 bit number corresponds to 1 and 0011 corresponds to 3. The condition may be sum less than or equal to 9 but carry is 1. That is overflow from fourth bit. Let us check the number 9 and 8 decimal number. Those are converted to BCD. 9 corresponds to 1001, 8 corresponds to 1000. So we will get the result 0001. This is not a invalid BCD. This is a valid BCD. But when you add this, see 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 1 is 0 and carry 1. So result is less than 9 but carry is generated. So actually it is a overflow from fourth column to fifth column. In that case, the result is incorrect and therefore the incorrect result will be corrected by adding 6 in the result, and therefore we will add here 0110, that is 6 in the sum, and then adding this you are getting the corrected result 0001, 0111, that is 17, and obviously 9 plus 8 is 17. Okay, here the following tree indicate the summary of the conditions. So whenever answer is incorrect, check the carry. The incorrectness of the answer can be adjusted by adding 6 to the result. Rest of the examples of BCD addition student can go through it. BCD subtraction can be done by using 9's complement and 10's complement method can also be done, but this is beyond the scope of your syllabus. That's all about the arithmetic operations on various number systems. So today we will stop here. We will continue our discussion of unit number 3 in the next lecture. Next lecture we will study the basic building blocks of digital electronics. Those are logic gates and Boolean algebra. So till then, bye bye friends. See you in the next lecture.